Title: Potassium Tungsten Bronze KWO3 Nanostructures for Near-Infrared Shielding Smart Window Applications, which is based on the work of Ms. Priya Dimri, Debya Sarkar, Dr. Himani Sharma, and Dr. Charu Dwivedi. Introduction: Smart windows are advanced glass systems designed to precisely control the amount of sunlight and heat entering a building. Unlike traditional windows, smart windows significantly reduce heat gain while still allowing visible light to pass through. This technology is a critical solution for energy saving, improving comfort, and ultimately supporting the move towards green and sustainable buildings. What is smart window? Smart window is a type of glass which is designed to partially block unwanted solar radiation. By controlling the solar energy passing through the glass, these windows achieve two major benefits. They help maintain higher energy performance level in building, and they keep the indoor temperature stable without the heavy use of air conditioning. Near infrared smart window: sunlight contains 50% NIR energy, which is responsible for heating indoors. NIR smart windows use special nanomaterial coatings to block heat carrying NIR radiation. This reduces air conditioning load, lower electricity bills, and improve indoor comfort. These coatings are passive, meaning they do not require any external power supply. This slide demonstrates how solar radiation contributes to interior heating, known as solar heat gain. Visible light passes through the window, but the interior surfaces absorb the energy and re-radiate it as infrared heat. Standard glass traps this heat inside, increasing the room temperature. This effect is why selection like using low eco coatings is vital for maintaining a comfortable and energy efficient indoor climate. This slide explains how a thermochromic VO2 film acts as a smart window, automatically booking heat when the film gets hot, while allowing visible light to pass through. The full system achieves multi-mode control for optimal building energy efficiency. The significance of the smart windows. It explains that since half of the solar energy is heat, which is NIR, standard windows derive up ACUs, consuming most of building's energy. Smart windows solve this by selectively blocking the heat while letting light through, significantly reducing cooling cost. What makes tungsten oxide essential? Tungsten oxide is essential for smart windows because it can strongly absorb heat while remaining transparent to light. Its properties can be optimized through doping, and it is a stable, cost-effective thin film material for energy-saving glass coatings. Potassium enhanced WO3. It describes how doping WO3 with potassium ions boosts the material's free electrons, which dramatically improve its ability to block heat. This modification, which also involves a favorable change in nanostructure, create a high-performance coating for energy-efficient smart windows. Synthesis procedure of KWO3 nanostructures. The hydrothermal method is a simple and low-cost technique was used to synthesize KWO3 nanostructure. The process involves starting with tungsten precursors, adding potassium salt to control the shape, and finally creating a thin functional coating on glass using a PVP binder and drop casting. This diagram visually summarizes the hydrothermal synthesis of KWO3 nanostructures. The key takeaway is that by adjusting the hydrothermal reaction conditions like temperature precursor ratio, the researchers were able to precisely control the resulting nanostructure shape, producing distinct nanorods, nanofiber for testing in smart windows. Characterization technique. There are five primary characterization techniques used to analyze the synthesized material. These techniques collectively cover the necessary data to understand material structure: XRD, HRTEM for composition, XPS, FTIR for stability, zeta potential, and most importantly, the optimal performance UV visible NIR essential for smart window application. Formation mechanism. The chemical route for WO3 nanorod formation via the hydrothermal method, Na2WO4 react with acid to form H2WO4, which then decomposes into WO3 nuclei. The rods form though anisotropic growth along one crystal axis with NaCl controlling the growth and Oswald ripening ensuring uniformity. Second mechanism is formation of WO3 nanoplates. It explains that L-positive tartaric acid is used to control the WO3 shape. Its functional groups bind to certain crystal faces, slowing down growth in those directions. This differential growth results in the formation of flat, plate-like nanostructures called nanoplates. Example of formation mechanism. The formation of the two KWO3 shapes, which is nanorods, are grown by agents like NaCl that promote one-dimensional growth, yielding long rod with high NIR shielding. Second, nanoplates or nanofibers are grown by using tartaric acid as a capping agent to block certain faces, yielding flat structures with strong optical absorption. Zeta potential and stability. The zeta potential showed that doping WO3 with potassium result in a more negative value. This indicates the KWO3 material has superior dispersion stability. This stability is vital for creating uniform thin films and maximizing the optical performance of the smart window coating. Optical and structural properties. The table compares the nanostructure showing the potassium doping effectively lowers the band gap, which improves NIR shielding in the nanorods, while nanoplates show the highest raw shielding. KWO3 samples, particularly the nanorods, achieve a crucial balance, which is a strong heating blocking with acceptable visible light transmission, confirming their stability for energy sufficient smart windows. The FTIR spectrograph confirmed the successful synthesis of the WO3 material by showing the characteristic WOW bond below 1000 cm inverse in all samples. Differences in high frequency region of the dope materials indicate that potassium has successfully modified the chemical structure, likely due to the incorporation of potassium ions or the resulting changes in the surface group. The Raman spectrograph confirmed the presence of the tungsten oxide and are used to study the crystal structure. The observed peak, shift and intensity changes in the KWO3 sample compared to the pure WO3 demonstrate the potassium doping was successful and resulted in detectable change in the crystallography symmetry of the nanostructures. The XRD patterns confirms that all synthesized materials are highly crystalline monoclinic WO3. Crucially, the data showed the potassium doping was successful, causing a slight shift in the characteristics WO3 peaks without introducing new impurity phases. This confirmed the incorporation of potassium ions into the WO3 crystal structure. This slide provides a visual comparison of the transparency and tint of the smart window coatings. It shows the pure glass baseline, the base WO3 coatings, and the potassium dope films. The image confirms the successful formation of uniform thin films and visually support the findings that potassium doped nanostructure offer high visible transparency, which is ideal for smart windows. These graphs confirm the smart window concept. All WO3 films effectively block heat compared to the plain glass. Crucially, the potassium doped nanorods show the best overall performance, demonstrating a strong combination of low NIR transmittance and acceptable visible transmittance, making them the superior coating. Morphological analysis findings. The analysis confirms that the hydrothermal synthesis successfully created distinct KWO3 nanorods and nanofibers. The XRD showed the improved crystallinity and the XPS confirms the desired potassium incorporation and the formation of W plus 5 states, which are responsible for the superior heat blocking performance of the smart window film. The images visually confirm the intended nanorod morphology for the WO3 samples, with image A showing a dense collection of uniform rods and image, while the B providing detail on the cross section and growth orientation of these rod-like structures. These images visually confirm the rod-like shape of the KWO3 nanostructures and demonstrate that increasing the potassium concentration result in the formation of longer nanorods compared to the lower concentration. The images visually confirm the fibrous web-like morphology of the WO3 nanostructures, demonstrating the successful formation of nanofibers as an alternative structure of the nanorods. Mechanism behind improved NIR shielding. Potassium doping improves NIR shielding by increasing free electrons to enhance the LSPR effect, reducing the band gap for greater NIR absorption and ensuring the stable dispersion for uniform high quality films. Understanding key results in goal setting frameworks. The results show the potassium doped is superior, offering the best trade-off between blocking heat between 76 to 83% NIR shielding and maintaining good daylighting, which is essential for energy sufficient smart windows. So the conclusion is the research concludes that the potassium doped nanostructures are superior, offering enhanced heat blocking and transparency. The successful use of a simple scaled method makes KWO3 a highly promising material for future energy sufficient smart windows. The future prospects are: future work will focus on fine tuning the potassium doping, testing other alkali metals like sodium and lithium, and scaling up the film development to create practical large area smart window for commercial use. This slides provide the bibliography for this presentation, listing the web links and academic sources from which the data, images, and technical details on smart windows were derived.